Okay, so yesterday we finished with the statement and proof of Euler's theorem. So there it is, boxed. So this is going to be really important for us going forward. As I mentioned yesterday, it turns out this is actually going to be the key, a key part of the next crypto system that we're going to talk about, which I'll start on later today. But anyway, so just reminding you, if n's a positive integer, b is an integer that's relatively prime to n, then b to the phi of n is congruent to 1 mod n. With phi of n, of course, being the Euler phi function of n. Okay, so we proved this yesterday. What was required was this earlier theorem that doesn't have a name in the textbook, but that I had given the name, the theorem using unique factorization to compute phi of n. This made proving Euler's theorem pretty nice once we had a lemma. Once we had this lemma that was similar to the lemma in the second proof of Fermat's little theorem. So anyway, so this theorem was all we needed, plus that lemma that I skipped the proof of yesterday to show Euler's theorem. So a couple of examples of applying this. So for instance, note that phi of 15 is phi of 3 times phi of 5. And this is easy enough to compute. So this is going to be 2 times 4, right? Of course, because 3 and 5 are both prime, so phi of 3 is 3 minus 1, phi of 5 is 5 minus 1. So this is 2 times 4, or 8, right? Now, I haven't used Euler's theorem yet, so Euler's theorem says that 2 to the phi of 15 is congruent to 1 mod 15, right? Since 2 and 15 are relatively prime, i.e., since phi of 15 is 8, this is saying that 2 to the 8 is 1 mod 15. Okay. So in fact, you can check that indeed 256 is congruent to 1 mod 15. Okay. All right. So this is one application of Euler's theorem. Of course, similarly, what about applying this mod 10? So phi of 10 is 4. Thus 3 to the 4 is congruent to 1 mod 10 by Euler's theorem. Of course, this is true because 3 to the 4th is 81. Okay. All right, let's apply this one more time here. So what are the last 2 digits of 3 to the 84? Okay. Of course, what we're really being asked when we're asked for the last 2 digits of 3 to the 84 is we want to know what is 3 to the 84 mod 100. All right, that's what I'm computing. Okay, so in order to compute 3 to the 84 mod 100, I note that phi of 100 is 40, right? Thus, by Euler's theorem, three to the phi of 100, that is 40, is congruent to 1 mod 100. Okay. Thus, 3 to the 84 can be thought of course, as 3 to the 40 squared times 3 squared. All right. So this is just me judiciously applying the division algorithm to 84. Okay, so this is, of course, congruent to 1 squared times 3 squared. Sorry, this is not 3 squared, this is 3 to the 4th. Bad at mental arithmetic. So this is 3 to the 4th here. So this is 1 squared times 3 to the 4th. 3 to the 4th, of course, is 81, so this is congruent to 81 mod 100. Thus, what are the last two digits of 3 to the 84? 81. Thus, 81 are the last two digits. Of 3 to the 84. Okay. Okay. So in fact, you may have caught something here that we did in this last example that reminds you of something that we have done previously using Fermat's little theorem. So actually, this gives us the following idea, which I can phrase as a corollary to Euler's theorem. So I have the following corollary. Let n be a positive integer so let n be a positive integer and suppose b is an integer with GCD of b and n equal to 1. So let it be an integer relatively prime to n. And if x is congruent to y mod phi of n, then b to the x is congruent to b to the y mod n. Okay. I like the way this looks under the camera. Maybe it seems fine on screen, but using the red ink's a little light, so I'm going to switch back to blue and black. Okay. So, how do I prove this? Well, I've already said it's a corollary of Euler's theorem, so it actually follows immediately from Euler's theorem. So, right, x is equal to y plus phi of n times k for some integer k. Right. All right, then, and why can't I do this? Just a quick reminder, of course, this is the definition of congruence mod phi of n. It's the definition of congruence mod whatever, right, is that you can express, this is just saying that the difference of x, y is a multiple of the thing, the modulus, right? Okay, so then what can I say here? Well, then b to the x is congruent to b to the y times b to the phi of n times k, which I can already write that in a nice way as b to the phi of n to the k. But you know where I'm going with this. By Euler's theorem, mod n, this is congruent to 1. So this is congruent to b to the y times 1 to the k, which is congruent to b to the y mod n. And so that's it. So all of this was the definition of congruence mod phi of n, and at this step I used Euler's theorem. Right, for that congruence. Okay, so I mentioned that you might recognize this from somewhere. This was also a corollary that we got from Fermat's little theorem. It's just this is a more general thing, right? This is a more general statement. So in fact, note if n is a prime, this corollary says the following. So if it's a prime and you have a b that is relatively prime to p, then which think about what that means, right? If p is prime, then you get that if x is congruent to y mod phi of p, but if p is prime, phi of p is p minus 1. So the corollary says x congruent to y mod p minus 1 implies b to the x is congruent to b to the y mod p, which was exactly this corollary of Fermat's little theorem. Okay. All right. So this new corollary of Euler's theorem we have is a more general statement, right? So it specializes to the statement that we were familiar with before if you substitute for the positive integer in here just a prime. Okay, this reduces to that previous corollary. Okay. All right. So a couple of examples of this corollary. And then I'm going to finish up with a proof of one of the things that I didn't prove that I said I would prove a bit later. So some examples of using this corollary. Let's say n is 15, then phi of n is phi of 3 times phi of 5, as we saw before. This is 8. And since 9 is congruent to 1 mod 8, then 2 to the 9 is congruent to 2 to the 1 mod 15. Okay. And we can check this. So in fact, 512 is indeed congruent to 2 mod 15. Okay. Okay. Here's another example. So let n be 10. Then phi of n is equal to 4. Okay. And since 5 is congruent to 1 mod 4, then b to the 5th is congruent to b mod 10. Exactly when what? What's the other assumption, right? So I went ahead with it here because because I could say that 2 and n were relatively prime, I need b to be relatively prime to n, which in this case is 10. Right? So this is true when the GCD of b and 10 is 1, i.e., if b is 1, 3, 7, or 9. Okay. So what does this say? Well, it says that b to the 5th always has last digit b if b is 1, 3, 7, or 9. Okay. But actually, this particular fact is true even when GCD of b and 10 is bigger than 1. Okay, so in this case, the last digit. So for instance, 2 to the 5th is 32. So 2 to the 5th has last digit 2, or is congruent to 2 mod 10. So you can actually check that this works in general. But this corollary of Euler's theorem at least allows us to immediately say this. Okay, another example. So let's suppose m is an integer with the GCD of m and 77 being 1. All right, so it's relatively prime to 77. Okay, so let C be congruent to m to the 7 mod 77. Okay. What is c to the 43 mod 77? Okay. Well, since phi of 77 is the same thing as phi of 7 times phi of 11, both of these are primes, and so this is 7 minus 1, this is 11 minus 1, so 6 times 10, so this is 60. Okay. And 301 is congruent to 1 mod 60. Okay. Then c to the 43 is congruent to m to the 7 to the 43, which is congruent to m to the 301, which is congruent to 1 mod 77. Okay, I'm going to stop for a second because there's a lot of stuff to keep track of here. So computing phi of 77 quickly is just using this fact that I'm going to prove soon, that if you have a product of integers and they're relatively prime, so for instance, if you have the prime factorization of an integer in front of you, computing its Euler phi function is really, really simple. So in this case, 77 is just 7 times 11. That's its prime factorization. So it's phi of 7 times phi of 11. Boom, that's 60, right? Because phi of a prime is prime minus 1. So this is 6 times 10, or 60. This, of course, you're like, why did I compute this first? I didn't. I did this and then noted, 301 is congruent to 1 mod 60. So this is the congruence in the first part of the corollary, right? This is the congruence mod phi of n in the corollary. Okay, and so this tells me about raising to power mod 77, which is the thing, which is n in this case, right? So so that's the deal. That's where this comes from. Okay, so thus C. Sorry, this isn't congruent to 1. This is a mistake here. This is congruent to m to the 1. So this is not right here. This is m to the 1. I wrote the exponent instead of what I was supposed to write here. Okay. So C to the 43 is congruent to m mod 77. Okay. All right. i.e. C to the 43 mod 77 gives back the original number m. This is actually an example of RSA encryption, decryption. Okay, so we'll see this later, but this is the first example you'll have of this RSA encryption. Of course, it doesn't make sense yet in this context because the actual algorithm I'm using to encrypt doesn't really make sense, but the fact that this is reversible from having integer m that is relatively prime to, say, 77 here, you will see where this comes in. The fact that C to the 43 is actually m, or C to the 43 gives back or recovers the m that you started with in this process. This is a key fact about RSA encryption. So as I said, we'll get to that by the end of class today. Okay. So here's another example of using this stuff. What is the last digit of 3 to the 7 to the 5? When you have a tower of exponents, of course, I mean this is 3 to the 7 to the 5th. It's not, 3 to the 5 times 7, obviously. So, if you're, if you were careless with the interpretation, or, when you're suppressing parentheses, using like an associative property or something, there's always this issue of when you have multiple operations here, where do the parentheses go? And so we don't want to have to write parentheses all over the place. So whenever I have a tower of exponents, it's 3 to the 7 to the 5th, right? That's how the association goes, right? So that's how the parentheses go. Anyway, okay. So when I want to compute the last digit of this, of course, this would be a pretty huge number. And so how do I deal with this? The idea is I want this 7 to the 5th to be something smaller. I want to reduce the 7 to the 5th somehow. And so the idea is note that phi of 4 is equal to 2, and 5 is congruent to 1 mod 2. So 7 to the 5th is congruent to 7 to the 1, which is congruent to 3 mod 4. Okay. All right. Again, quickly keep track of what it is we're doing, right? So if phi of 4 is 2, the exponents in this eventual statement need to be congruent mod phi of 4. In this case, congruent mod 2. So then congruence of the exponents mod phi of n yields congruence of b to those, b to the x and b to the y mod n. So in this case, my exponents 5 and 1 are congruent mod 2, which is phi of 4. So then 7 to the 5th and 7 to the 1 are congruent mod 4. Okay, so 7 to the 5th is congruent to 3 mod 4. And since phi of 10 is equal to 4, well, that's nice, then 3 to the 7 to the 5th is congruent to 3 to the 3, which is 27, which is 7 mod 10. Why? Well, phi of 10 is 4. My exponents 7 to the 5th and 3 are congruent mod 4. Thus 3 to the 7 to the 5th and 3 to the 3 are congruent mod 10, since phi of 10 is 4. Okay, so the last digit of 3 to the 7 to the 5th is 7. Okay. All right. So, last thing I wanted to do in this section is return to that proposition at the beginning that is very important. If GCD to positive integers m and n is 1, then phi of mn is phi of m times phi of n. Okay. Now, this is a slightly annoying proof. It's actually a simple proof, but it is unlike most of the other proofs we've done in this course, because it's more of a proof about counting the members of these sets that we're going to define. Okay, and really what it is, this is something that could have been given to you in your first proof course when showing something about one-to-one correspondence. Now, I'm going to avoid using that language here, even though that's exactly what's going on. So I will make note of it. I will bring up, how I could rephrase these things in terms of thinking about bijections between two sets. But I'm not going to do it that way. I'm going to be more wordy than that. Okay, so what is the idea here? The idea define the following sets. Okay, so the first set is S sub 1 of mn, and this is defined to be the set of pairs AB such that A, that's the first slot in the pair, is between 1 and m. The second slot in the pair is between 1 and n. Okay. And the GCD of A and m is 1. And the GCD of B and n is 1. Okay. So that's my first set. Okay, so what is this? This is the set of all ordered pairs of integers a and b, such that a, the first slot, is between 1 and m, b, the thing in the second slot, is between 1 and n, a is relatively prime to m, and b is relatively prime to n. So really, these things are being put together independently, right? These slots are actually kind of independent to one another. The first slot has to do with its relation to m, and the second slot has to do with its relation to n. In fact, this is a finite set, of course. So given an m and n, this is a finite set. If it's a finite set, it has a finite number of elements, and I can just count them, right? I can just list out all the elements that I want to. So let's think. The first slot here counts all of the integers a between 1 and m that are relatively prime to m. Nothing else about this definition affects that first slot a. So the first slot is entirely determined by its relation to the integer m, right? So the number of possible a's here in my ordered pair is the number of integers a between 1 and m that are relatively prime to m. Well, how many of those are there? There's phi of m, right? That's exactly what phi of m is. Phi of m is the number of integers between 1 and m that are relatively prime to m. Okay, so in the first slot, I have phi m possibilities. All right, so first slot, phi of m possibilities. And in the second slot, how many possibilities do I have? Well, in the second slot, this is counting the total number of integers between 1 and n that are relatively prime to n. So that's phi of n possibilities. And now I know when you were in elementary school, multiplication was not exactly phrased to you as counting ordered pairs, right? But of course, that's exactly what it does, right? Maybe it was phrased to you as, groups of, boxes of apples or something. But the point is that the the idea here is if I'm counting the total number of elements here, these slots are independent of one another. There's no interference between the slots. So the first slot gives you phi of m possibilities. The second slot gives you phi of n possibilities. So what's the total number of elements of this set? It's phi of m times phi of n. Okay. Okay, and so the total number of elements of that set are phi of m times phi of n. Okay. Now you might say, well, okay, I kind of see where you're going with this, but why would you do it this way? And I'm going to punt that question until I define the next set. And then we're going to do some examples, and I will show you why we're doing it this way. Because it turns out there's an issue with what we'll see arises out of order. The order that things occur in are not exactly the like obvious order. And so we would have to make arguments about the order and rearrangement of stuff, and we don't want to do that. It's actually easier to do it this way because, as it turns out, and as a lot of you probably already know, when you're dealing with finite sets, the order of the elements doesn't matter. So if I have in fact, not just the order, but the labeling in the sets. So, for instance, I had two finite sets, 1, 2, 3, 4, and A, B, C, D. Those are the same set in some sense, right? Now, I'll punt until give me like 10 minutes and I will get into that discussion. But that's exactly the reason why we're doing this. Okay, and so the important thing here is that phi of m times phi of n is the total number of elements of this set. Okay, so I have another set that I want to define. So I have the set S sub 2 of mn, and this is defined to be the set of all x such that x is between 1 and mn, and the GCD of x and mn is 1. So this is more straightforward to compute the total number of elements. So the total number of elements, this is the number of integers between 1 and m times n, such that that integer is relatively prime to m times n. So total number of elements is phi of mn. Okay. All right, so if we can show that the sets S sub 1 of mn and S sub 2 of mn have the same number of elements, we will have shown that phi of mn, which, since that's the total number of elements of S sub 2 mn, is equal to the total number of elements of S sub 1 of mn, which is phi of m times phi of n. Now, as I said, you may say this is a really roundabout way of doing it. Like if I could show that those two sets had the same number of elements, then that's kind of exactly the thing I'm trying to prove. Anyway, how does this help me? Showing two finite sets have the same number of elements. Okay. What this means in the language of set theory, so note in set theory language, this is saying that the sets S sub 1 of mn and S sub 2 of mn are in one-to-one correspondence, i.e. that, what does this mean? That there exists a bijection. I'll use the letter F. Between the two sets. What's a bijection between two sets? So it's just a function between the sets that's one-to-one and onto. Okay, so it is injective and surjective, right? So F is one-to-one and onto. These requirements will be rephrased in this proof. Okay, so to answer your question of why we would go about it this way rather than something you might consider a more direct method, is that rather than actually trying to think about abstractly how to like count these elements or match them up, what we have to do is we can construct this function, this bijective function that matches the elements. And then if we show that this function is one-to-one and onto, we're done. Okay, so our proof of the proposition will be the construction of this bijection F. Okay. And it won't take too much effort technically, but it does actually involve the Chinese remainder theorem, as we'll see. So Chinese remainder theorem is the way to define one of the directions of this bijection. Because another thing that's equivalent here that you probably already know is that whenever you have a bijection like this, a bijection implies the existence of an inverse function so if you have a bijection mapping from set S1 to S2, there's also a bijection mapping from S2 to S1 that's the inverse function for that thing. Okay. And you have that the second you have this thing's 1-to-1 and onto. Okay. So before I get into the proof, I want to do an example to illustrate this. Okay. So first, an example to illustrate what's going on. Okay. So I think it's important to see this proof, to see a particular type of bookkeeping that goes on with this stuff. Okay, and so to see what it is that's happening here, let's let M be 4 and N be 5. Okay. So let N be 4 and M be 5. Then we can just list out the elements of S sub 1 of 4, 5 and S sub 2 of 4, 5. So S sub 1 of 4, 5, let's remember our definitions. So S sub 1 of Mn is the set of ordered pairs where the thing in the first slot is an integer between 1 and m, relatively prime to m. And the thing in the second slot is an integer between 1 and n, relatively prime to n. So all possibilities for A and B are ran through here. And so anything in my first slot is going to be an integer between 1 and 4 that is relatively prime to 4. Well, 2 and 4 are not relatively prime to 4, so the only other possibilities are 1 and 3. So my first slot is always going to be 1 and 3. 5 is prime, though. So in my second slot, I have integers between 1 and 5 relatively prime to 5, so I have everything except 5. So 1, 2, 3, or 4 is allowed. So another way of writing this is the set of ordered pairs AB such that A is either 1 or 3 and B is 1, 2, 3, or 4. Okay, so writing that out, this is 1, 1, that's fine. 3, 1 is fine. The next one is 1, 2. And the next one is 3, 2. And the next one is 1, 3. And then 3, 3. And lastly, I have 1, 4 and 3, 4. Okay. And we can quickly check. This has 8 elements. Is that phi of 4 times phi of 5? Well, it is, yes. So it very much is. So note 8 is equal to phi of 4 times phi of 5. Phi of 5 is 4. Phi of 4 is 2. So 2 times 4 is 8. Okay. All right. So this is the size of S sub 1, 4, 5 is 8, which is, I'll rewrite it like this. Okay. All right, and S sub 2 of 4, 5 is, well, remember our definition of S sub 2 is all the integers between 1 and m times n that are relatively prime to m times n. So that is the set of integers between 1 and 4 times 5, so 20. Set of integers between 1 and 20 that are relatively prime to 20. Well, I can quickly list those out. That's 1, 3, 7, 9, 11, 13, 17, and 19. Boom. There they are. Okay. Note, those there's the same number of them, right? There's 8 of them. And note the size of S sub 2 of 4, 5 is 8, which is the same as phi times 20. or phi of 20. Okay. Okay. Now, our proof aims to match up the elements of these two sets via some map bijection, really. Okay, I'm not even going to give it a name when I do it in the proof. So what is the idea here? Okay, so the idea is the following. So here's the proof, or the beginning of our proof. So let AB be an S sub 1 of Mn. Okay. By the Chinese remainder theorem, there is a unique element. So there exists a unique element X mod Mn with X congruent to A mod M and X congruent to B mod N. We can always choose the lowest or the least non-negative congruence class, right? The least non-negative residue class. And so we can always choose this X to be between 1 and Mn, right? And we call this X sub AB. Okay. Okay. All right. And so what is going to be my map? Then the idea, let my bijection be the thing that takes AB and sends it to XAB. Okay. All right. And so in this way, we'll see that it is going to map from our first set, which contains ordered pairs of integers AB, to integer between 1 and Mn that is going to be relatively prime to Mn, as we'll see. So this is going to be the thing that does it. So actually, if we were using really slick set theory notation, we could be done in like a couple of lines. But I'm going to go through this acting like I'm not really doing that, so that I'm explaining what's going on in terms of absolutely everything that we've done up till now. Okay. So first, want to do an example, what it is that's going on in terms of our example. So in particular, X sub AB satisfies the following equations. X sub AB is congruent to A mod M, and X sub AB is congruent to B mod N. Okay, and this is unique mod Mn, right? So, returning to our example, this is an aside. So returning to our previous example. So, looking at our previous example. Okay. So here's letting m be 4 and n be 5. Here's my list of ordered pairs in S sub 1, 4, 5. And here's, of course, my list of elements in S sub 2, 4, 5. So let's go through my ordered pairs. So what is x sub 1, 1? Okay. All right. What is x sub 3, 1? Well, for instance, what am I saying here? X sub 3, 1. I'm looking for, so let's go aside here. X sub 3, 1 would need to satisfy, so it would need to be congruent to 3 mod 4, and it would need to be congruent to 1 mod 5, right? Okay. So what integer between 1 and 20 is congruent to 3 mod 4 and 1 mod 5? So I divide by 4, it has remainder 3. I divide by 5, it has remainder 1. Turns out that's 11. Okay. Okay, so 11 satisfies that. And I can say that it's equal to 11 because this is unique mod mn, and I can pick the least positive or the least non-negative residue class, right? Of course, all these are going to be at least 1. In fact, x sub 1, 1, since it has to be congruent to 1 mod 4 and 1 mod 5, that is unique mod 20, and that's just 1. What about x sub 1, 2? Sorry. What's x sub 1, 2? So it's congruent to 1 mod 4 and 2 mod 5. Well, that's 17. And what about x sub 3, 2? Well, that's congruent to 3 mod 4 and 2 mod 5. That's 7. And the next one, x sub 1, 3, is congruent to 1 mod 4 and 3 mod 5. That's 13. And x sub 3, 3 is congruent to 3 mod 4 and 3 mod 5. Well, that's 3. And x sub 1, 4 is congruent to 1 mod 4 and 4 mod 5. That's 9. And lastly, x sub 3, 4 is congruent to 3 mod 4 and 4 mod 5, so it's 19. So what is this? Well, again, looking back at my example, I've given myself not enough room. There we go. So looking back at my example, this associates to each ordered pair in S sub 1. All right, so here's S sub 1. Here's every ordered pair in S sub 1. Every ordered pair shows up in these subscripts and gets associated to some thing in S sub 2. All right, it gets associated to one of these elements. But it doesn't get associated in order, okay? And so that's the thing that this approach makes so nice. It doesn't actually matter the order that it gets associated in. The only thing that matters, that I'm going to write out here in a second, is that this association is one-to-one and onto, right? Which means that I can't have, so being one-to-one means that one thing gets assigned to one thing. I can't have two distinct ordered pairs getting assigned to the same thing over here. That is going to cause issues going backwards. And it's going to mean that the sets are not going to have the same number of elements, because that's ultimately what we're proving, that they have the same number of elements. And then going in the other direction, I need to make sure that every single thing that shows up here is associated to some ordered pair, or else there would be too many over here. Or sorry, there'd be too many over here that it doesn't come from something in the ordered pair set S1. Okay, and so this maps each ordered pair to something. It matches up every ordered pair to something in this list, but it just doesn't do it in this order, right? And that's fine because we don't care about that. What's important is the one-to-one and on-to-ness of this thing. Okay. So since these are matched up exactly, again, as I said, it's one-to-one and onto, then these sets have the same size. I.e., of course, what that says is that phi of 20 is equal to phi of 4 times phi of 5. Okay. But we can do this in the general case. So this is an aside. Let me extract this from the proof by boxing it in. So that's not a part of our general thing. So proof continued. Start with AB in S1 of Mn and associate to it X sub AB, okay, which is in S2 of Mn by definition. Okay, so our two questions. If we can answer these questions in the affirmative, or actually depending on how I phrase them, whether it's affirmative or negative, but if we can suitably answer these questions, then we're done. So our two questions. One, can different pairs AB be mapped to the same X sub AB? And two, is every X in S sub 2 of Mn associated to some ordered pair? Okay. So, as I said, you might recognize one is one-to-oneness, and two is onto-ness, right? So the first one is injectivity, and the second is surjectivity in the language of set theory. Okay. All right. So we're almost done. So again, proof continued. For question 1, okay, if A sub 1, B sub 1, and A sub 2, B sub 2 are both matched to some X sub AB, okay, that is the same element in S sub 2 Mn. Then X sub A1 B1 is equal to X sub A2 B2. Okay, but A sub 1 is congruent to X sub A1 B1, but then that's equal to X sub A2 B2, and that's congruent to A sub 2 mod M. I could have a similar congruence mod n, and I'll say that in a second. Okay, so we get that the first two in the slots are congruent mod m. So a sub 1 is congruent to a sub 2 mod m. But 1 is less than or equal to a sub I is less than or equal to m, right? For any I, right? There's only two choices here, 1 and 2. But the idea is both of them are between 1 and m, so they actually have to be equal if they're congruent mod n. So a sub 1 is equal to a sub 2. And similarly, b sub 1 is equal to b sub 2 using the other congruence. Right? So using the other congruence. Okay. And so this answers our question, can two distinct ordered pairs be matched to the same x sub ab? The answer is no, because it turns out they weren't distinct ordered pairs. They were actually the same. Okay. So that mapping that we have created is one-to-one. Okay. Or it is injective. So our association that maps AB to XAB is one-to-one. And two, lastly, let X be an S sub 2 Mn. Define the ordered pair AB with A between 1 and M and B between 1 and N by A is congruent to X mod M, and B is congruent to X mod N. Okay. So to see that this X always comes from some ordered pair, AB, what do we have to do here? So since M divides Mn, then the GCD of X and M has to be 1. Okay. This is actually an exercise in chapter 2. What exercise is it? It's exercise 61. Okay, this statement. Okay. So since X is congruent to A mod M, then GCD, and GCD of X and M is 1, then GCD of A and M is 1. Similarly, GCD of B and N is 1. And so, given an X, we can set up this pair of congruences that defines an ordered pair AB with A and B between M and N respectively that are relatively prime to M and N respectively. Okay. All right. Okay. Now, CRT implies uniqueness of this assignment. Of this association mod Mn. Okay. So we're done. Okay. So let's go through why exactly we're done. We've shown that these things can be assigned to one another in an unambiguous way that is one-to-one and onto. I'm not overcounting or undercounting. These two sets I've defined, S sub 1 and S sub 2, have the exact same elements. Okay, the same number of elements. Because they have the same number of elements, and because individually we can count what that number of elements is. So S sub 1's total number of elements is phi of m times phi of n. S sub 2's total number of elements is phi of m times n. Then phi of m times n has to be equal to phi of m times phi of n. And that's how this goes. Okay. So as I warned, that was a more annoying proof than some that we've done before, just because the process seems a little different, even if we're not really using anything high-powered or anything. It's just a kind of a question of organization here. Okay, and so I wanted to quickly mention, and I should also be able to finish the proof of this fairly quickly. So the last thing I wanted to talk about in Chapter 8, which is kind of a neat fact. So this is the last named thing after Euler's theorem. So this is Wilson's theorem. So Wilson's theorem has actually been known for like over 1,000 years, but I don't think the first proof of it, it was in 1771, was the first actual published proof of this. So I believe what's funny is the person it's named after, Wilson, couldn't actually prove it. It was proven later by Lagrange. So let P be prime, then P minus 1 factorial is congruent to minus 1 mod P. Okay. All right. So before I prove this, let's do an example that illustrates what it is that's going on here. So let P equal 7. Then P minus 1 factorial is 6 factorial. Right. 6 factorial is 720. And indeed, that is congruent to minus 1 mod 7. Right. Well, how do you know that quickly? Well, it's 720, right? This is like, if it were 721, it would be divisible by 7. Right? That's 103. And so it's 720 instead of 721. So it's 1 less than 721. So it's minus 1 mod 7. So yeah, okay. That's indeed how that works. But to actually see why this works, let's note a particular way of arranging this, right? So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. That's how factorial is defined. But I can arrange these in a funny way. I can arrange these as 6 times 5 times 3 times 4 times 2 times 1. Yeah, no, you might say, okay, you can definitely do that, but why would you want to do that? Okay, well, the reason that I want to do this is that if I look at these pairings here that I've made, I haven't just done this randomly. I could have paired 5 and 2 and 4 and 3. Okay, I could have paired 5 and 1 and 4 and 6 and 3 and 2. I could have done this pairing in any way I wanted to. Notice I left 6 and 1 unpaired. Okay, and so what is it that I'm doing here? Well, it turns out that what I'm doing here is pairing each of these up with their multiplicative inverses mod 7. Okay, so this is congruent to minus 1 times 1 times 1 times 1, so that's congruent to minus 1 mod 7. So here I'm saying 5 and 3 are multiplicative inverses mod 7. And 4 and 2 as well. Okay, so 5 and 3 are multiplicative inverses mod 7, so it's 4 and 2. Okay, so idea, prove Wilson's theorem. Via pairing numbers in p minus 1 factorial with their multiplicative inverse. Okay. Okay. So proof. Okay. So note, if b is an integer between 1 and p minus 1, then b times x is congruent to 1 mod p always has a unique solution x with x between 1 and p minus 1. So if you had any initial doubts as to whether or not we could do this in general, like we did in the example, well, since p is prime, right, the requirement that we need in order to always be able to solve this linear congruence for the multiplicative inverses, this always has a unique solution. Okay, up to p minus 1. Okay, and so we compare each integer with its multiplicative inverse mod p. Okay. So, of course, the way that this works is we're not double counting here. So if x is a multiplicative inverse of y, then y is the multiplicative inverse of x. And so x getting paired with y means that y gets paired with x. And so that pairing only has to happen once. You take the two integers and you pair them together, and then it's done. Okay. And the question is, this is fine, except some integers, b, get paired with themselves. Okay? When does this happen? When does this happen? Well, so the proof continued. Well, this happening means that b and b inverse are congruent, i.e., b squared is congruent to 1 mod p. We have solved this congruence for b before, though, right? This was actually a corollary of our solving linear congruences fact, right? Forever ago, back in chapter 6. So, the only times this happens is when b is plus or minus 1 mod p, i.e., when b when b is equal to 1 or p minus 1. Okay. No, equal to, not congruent, I meant. And that statement's also true, but when b is equal to 1 or p minus 1. And so, just like in the example, we can always do this except at the bottom of the factorial when b is 1 and at the top of the factorial when it's p minus 1. But at p minus 1 is when it's congruent to minus 1 mod p, right? So each number in p minus 1 factorial gets paired with its multiplicative inverse mod p, except for b equals 1 and b equals p minus 1. So p minus 1 factorial is congruent to p minus 1 times 1. Everything else cancels because it gets paired with its multiplicative inverse mod p. So everything in between here is 1 in that product. And so this is just p minus 1 times 1, which of course is congruent to p minus 1, which mod p is congruent to minus 1. Right? Okay. So it took us a few minutes to write out, but in terms of actually, what was said, we could have basically done that in like 2 sentences. So this actually, interpreting this in another way, we could say that this gives us a primality test, but it's kind of pointless. And the reason it's pointless is because computing factorials is terrible. Factorials get huge really quickly. And so computing factorials is absolute garbage. And so this is not a very useful primality test. So a somewhat useless primality test follows. So this is a corollary of Wilson's theorem. Let n greater than or equal to 2 be an integer, then n is prime if and only if n minus 1 factorial is congruent to minus 1 mod n. Okay. So I will skip the proof. You can have a look at that. So this is on page 202 to see how this follows from Wilson's theorem. So basically the thing is that if n is actually composite, then this thing has to be congruent to 0 mod n. So yeah, since n minus 1 factorial is actually divisible by n if n is composite, so the only way that this works out, if this is congruent to minus 1 mod n, then n has to be prime, is what this ends up saying. So anyway, why I said that this is somewhat useless is just because computing n minus 1 factorial, if you have some gigantic prime n, computing n minus 1 factorial takes so long and is so horrific that this is all but entirely useless for computing whether or not something is prime, because that computing n minus 1 factorial is a way worse question than you even want to answer. So that's the reason for me saying this is somewhat useless. Okay, so that is all of chapter 8. So I anticipate finishing chapter 9. I won't entirely finish it by Friday. I will have done a good chunk of it. The meat of it I'll actually be able to do mostly tomorrow. But I would say by Monday or Tuesday next week I'll be done with chapter 9. We'll be moving on to chapter 11. So anyway, stay tuned, and I will see you all